Yeah. So it's a pleasure to introduce Kasturi from IIT Bombay. So just a very brief bio. Kasturi did her BSc in physics from St. Stephen's College and then MSc from IIT Delhi. After that, she did her PhD at Cornell with Alexander Gaeta in the applied physics department. And then she was a postdoc at MIT with Paula Capillaro. And then after that, she joined Bombay in the Department of Electrical Engineering. So before I tell her her research interests, which I know is related with color defects in diamond, Kasturi was actually the first person in India to actually start an experimental program. And I can tell you, starting something where nobody else works in this country is not easy. So she has now developed a vibrant research program with this. And right now she's working on various aspects of this field, including quantum sensing, nanophotonics, precision metrology, and quantum computation with solid state.
Thank you, Mr. Ghosh, and thank you, Akshay, for giving me this opportunity and this invitation to come here and meet you all and talk about a little bit about the work that we're doing in IIT Bombay. Yes, as Prof. mentioned, that this is the first time in India we've set up a wide field microscope, and indeed it has been quite challenging to get to this position where we can actually do some microscale magnetic field sensing with color defects in diamond. And so today, my talk will focus on this microscale magnetic feature imaging. So let me just directly go on to the meat of my talk, essentially. Yeah. So as you all are aware that India is focusing a lot on quantum technologies and developing indigenously various kinds of quantum technologies, including quantum computing and quantum sensing. We have been focusing a lot on quantum sensing. However, quantum sensing has been prevalent for quite some time, especially if you look at available diagnostic tools, and you might not be aware of it, but it is existing in various forms. For instance, PET and OCT. These are two examples where you actually use really the quantumness, the true quantumness in its essence. And of course, MRI machine is all very well known. This is the product of our first quantum revolution, of course. And then there are two other examples which I really like, which is the optical clock. We all use GPS. We know the importance of our optical clocks. And then there is LIGO, which uses squeeze light. So that's another example, a fantastic example of where quantum sensing and metrology really plays a key role in various kind of useful devices. So now I will focus on magnetic field sensing. So as you can see here in this plot, it's a sensitivity versus linear sensor dimension, or one can think of it as resolution of the sensing. Okay, so if you see here, you find various different kind of platforms which are available for sensing a magnetic field. As you know, magnetic field can scale in physical systems around us. It can be of the orders of picotesla, which is 10⁻⁻12 Tesla, to very high fields like several Teslas, for instance, in magnets that are used for MRI machines, and these are like 9 Tesla, 11 Tesla, and you can have various other applications where you need very high fields. Right, so you need sensors which can, sense the very tiny fields, whereas very high fields, right? And then you also need sensors that can not only sense the field, the magnitude of the field, but can also give you spatial resolution to see the variations of the fields. So they form a lot of different kind of application domains, and therefore one can immediately imagine that not one sensor will be able to satisfy all these criteria. So you have a whole bunch of different kind of platforms which come up with a different sensitivity number and also the kind of resolutions that they can provide. right? If you see in this chart, you'll find that the squid sensors or the atomic vapor cell sensors are really the best magnetic field sensors, which will sense of the order of picotesla or femtotesla level fields. And just to give you sort of a number, benchmark, Earth's magnetic field is of the order of, say, 50 microtesla or so, right? So 0.5 Gauss, right? So it's well below femtotesla is well below Earth's magnetic field, and so these kind of atomic vapor cell or squid magnetometers are really the best magnetometers available. Now, the platform that I will be telling you about is the NV-centered magnetometer, and these guys are, although not at femtotesla level, is about tens of picotesla has become sort of the benchmark number for these NV-centered magnetometers. But one of the key advantages of NV-centered magnetometers is the other scale that is prevalent here, which is the resolutions that we can use to measure. So if you want to look at spatial changes or spatially dependent magnetic field, then NV centers become a really important tool and important device where you can actually image different magnetic features with NV centers, because they can not only operate in widefield geometry but also in the scanning geometry. So you can actually have a tip like an AFM tip, which will have these NV centers, can scan over and give you different profiles. And this is one of the key advantages of having such NV center devices, magnetometers. Now,
what is the SCRF?
Sorry?
What is the SCRF?
These are surf. I don't remember exactly what the surf exactly means. These are also kind of atomic vapor magnetometers.
So high pressure metals.
Yes.
Resonating.
Yeah. So these are also atomic magnetometers. Yeah. So of course, people have been, always the push is going from a bench top or a tabletop system into a really small scale portable device, because ultimately, if you want to, take around a magnetometer and measure, say, Earth's magnetic field anomaly, that's one of the very big examples where one can apply such sort of magnetometers. Is essentially if you have, say, why do you want to measure anomaly in Earth's magnetic field? A key example is if you have an oil field and there is to detect the presence of oil, it actually identifies this sort of Earth's magnetic field. So one of the applications of such magnetometers is to do Earth's magnetic field anomaly test. And for that, of course, you can't have things sitting in your lab, right? So you need to have handheld portable magnetometers. And one of the biggest push towards such sort of magnetometers was even in magnetic field for biological sensing. So NIST developed this sort of a small portable magnetometer, which was built using atomic vapors. Okay, and these sort of handheld portable devices are very, very key for magnetic field measurement applications. Right? Now, of course, nobody likes working with vapors. It's always a little bit challenging. And so one would always like to extend and work towards a solid state device where things are not moving around, right? So you don't want things shifting. And atomic vapor cells, in contrast to that, the solid state devices are always sort of, useful, or at least we think will be useful for future. And so NV centers play a very key role there, because you have a solid state device, which is diamond, and one can have a handheld portable magnetic field sensor. So one can, people are now working towards these integrated full-scale portable magnetometers, especially in MIT, and there is also a few groups in US as well as Germany who are working towards these sort of portable devices. In fact, we also work on some of these portable devices. And another key application where portability helps is if you have a spin and then you have some molecules close to the spin, you can actually look into the dipolar interaction and map out the molecular structure. So these are some of the examples where NV centers play a prominent role. So today in my talk, I'll start with a brief introduction of MD centers just to get everybody on the same page. Then tell you about the different kind of applications of quantum sensing. I thought it would be nice to actually show what people have been doing globally for MD centers, especially for sensing. So just sort of give you some highlights of the variety of applications that are available for MD centers. Then talk about the dynamic wide field imaging that we have developed in India for the first time, not just in India, globally. This is the first time a dynamic wide field imager has been developed. And then some other highlights of some work that we've been doing. Jumping straight down into defective diamonds, you're probably all familiar with these very nice looking, bright, pretty, shiny diamonds. But of course, there can be colored variants of such diamonds, and that's primarily because you have some defects in them. And if you go to a gemstone store, they will actually sell it in the other way around. They'll sell the not so defective ones with some price, but the defective ones at even higher prices because they have colors. So it's actually, these are much more pricier than even the real, the very bright, clean diamond. Not always true, but most of the time. So it turns out that nitrogen, actually, if you have a lot of nitrogen concentration in diamond, it gives you a nice, bright yellow color to the diamond. And if you have nitrogen plus vacancy next to it, so if you look at this is the diamond lattice structure, you can see the nitrogen has substituted the carbon atom in its location. And then if you just have a vacancy next to it, along with one additional electron that is captured from the lattice, together it forms what is known as the Ap- complex. And this fluoresces in the red spectrum region, and so it actually gives it a nice pink color. So if you heard about the pink star diamond, this is actually the one that has NV centers. That's the pink diamonds are the ones that are the most prominent ones which have NV centers in them. Okay, so what are the different kind of, what you do with these sort of diamonds? People have done a lot of things with them. You can make nano diamonds out of them. So you essentially have powdered diamonds, which are of the scale of, say, 30 nanometer, 50 nanometer, 120 nanometer size, particle size. So you can do a lot of experiments with them. Then there is a variant which is the CVD grown or HPHD grown version. These are like glass plates. If you just look at them in the lab, they almost look identical to just a glass slide. And I've told my students, be very, very careful, because if you drop them, there is no hope that we will find them back again. So this is extremely difficult because they almost look like this. Then you also have whenever you see a substrate like this, you always want to do more than just the substrate. So you start patterning them and etching them and doing all sorts of things. And so people have started making these sort of devices like, pillars, and, you can make resonators and a whole bunch of other things. And then, of course, you can pick them up as a tip and put it on the AFM tip and use it like a scanning probe method. And so these are all the different kinds of variations in which diamond has been used, and NV-centered these diamonds have been used. Of course, you can also have the variety in the lab, which will have a lot of nitrogen content in it. It looks very yellow like this, and also the blue one, which looks like in the gemstone quality, looks like this. In the lab, actually looks like this. Let's understand how this NV center really works. What we do is we have to shine a green laser, and that excites the NV centers. This is the electronic structure. Here you have a ground state triplets. You also have an excited state triplet, and then there is a metastable state here. So when you use this green laser, it excites these NV centers inside the lattice, and then the NVs can go from the ground state to the excited state and fluoresce, and the zero phonon line is actually 637 nanometers. So this red light is 637 nanometers and above. And so what you can see is a very broad spectrum from 630 onwards. Okay, and this is a ground state triplet with the zero field splitting, which is 2.87 gigahertz. The plus and minus one are degenerate at zero magnetic field. If you apply a magnetic field, these two will split, and it gives you a nice 3-level system here, or a pseudo 2-level system, because you can drive the transition either between 0 minus 1 or 0 plus 1 and use it like Cupid, right? Now, what are the interesting properties of this sort of diamond is that when you actually shine like a bright diamond which has a lot of NV centers in them, it fluoresces really bright orange, and you can see them that the light actually comes out from the sides of the diamond, and that's because that the fluorescence gets trapped inside the diamond. Diamond is highly refractive in depth material, so it really, there's a lot of total internal reflection, and then the light actually comes out from the edges of the diamond. This is a very nice property of the ensemble dense NV center samples. But then what you can also do is take a confocal image. This has been done in our lab, where you have a sample which has sort of spots of these NV centers in them. And so what you can see are these bright spots, which are actually maybe 2, 3, 4 NVs in them. And there could be also singles in them. For instance, this one here, we have imaged here. This is actually a single NV center. You can do the confocal imaging, and of course, later on you can do a lot more calibrations, and you know exactly that this is a single. We know that this is a single here. So a single NV.
Sorry. So could you please elaborate how do you know that it is 1 or 2?
How do we know? The technical way of knowing whether it's 1 or 2 is actually to do the correlation, G2 correlation measurement, which is essentially you just have to perform the 2 split between splitter and then do the coincidence counting, and then look at, because every time you excite, it exactly de-excites as a single photon. So you can always measure if it's a single NV, you will know that it will emit a single photon. So that's how we know it. But we know it from another way, which is essentially, if you look at this, and I'll just come to that, is that if you have an NV center, this N can be in any of the 4 arms, right? So I'll just, maybe in the next slide, I'll explain exactly. There's an alternative way of knowing whether it's a single or a multiple. So, yeah. Yeah. Should I continue or?
Good.
Yeah. Okay. So first I'll explain the magnetic field measurement. So when you apply a magnetic field, essentially what happens is that the plus and the -1 degeneracy is broken. Now, what is interesting about NV centers is that the ground state actually fluoresces much more than the plus and the -1 levels, and that gives us a spin-dependent, optical contrast. And so we know exactly if an NV center was in the system 0, then you get a higher fluorescence. So if you look at this map, let's say we are at this stage. So we have the system polarized. So essentially it will always polarize. So if you keep shining the green light, it goes to this metastable state and always comes down to this 0 state. Or if it were in plus -1 state, it will just go to a metastable state and then always flip down to the 0. And it allows us to polarize the system just by shining green light. And also through the green light, we can know exactly what is the spin state, because the fluorescence contrast tells us whether it is 0 or plus -1. So what we do is we start looking at the fluorescence. If suppose we polarize it, we look at the fluorescence and we mark it on let's say this fluorescence versus microwave frequency, we just mark at some point on the fluorescence, right? And as we sweep the resonance frequency here, you see that there is a dip. So that dip basically corresponds to the resonant frequency, which we call this as the transition between 0 -1 or 0 +1. Right, so that's how we calibrate our system, and each dip corresponds to essentially a single transition. Right, so if you have a single photon, so if you see only one transition corresponding to this level and one corresponding to 0 -1 level, that will exactly tell you that there is one single NV center there. So essentially, this is an indirect way of knowing whether there is, but of course, the hard test is to just do the G2 measurement, and it will tell you whether this is a single or multiples. Okay. You can also have multiples in various different directions of the NV center.
So you were saying that 2 of them cannot have exactly the same spelling, 0 to they cannot have 2
No, 2 of them are very unlikely. Within a spot, 2 of them are very unlikely to be in the same direction. So one nitrogen axis is very unlikely that you will have 2 of them within the same 250 nanometer spot. So that's why I said it's an indirect probe. It's not a real. The real method is actually to do the G2 measurement. Yeah. So we can also know if there is a shift in this BZ field, then essentially these two lines will move, and so you'll see a shift in the resonance frequency, right? And that's how we actually do measurements of any kind of magnetic field, because this is an electron spin. So gamma is very well known. It's 2.8 megahertz per Gauss. So if you can measure this frequency shift, you know very well what the magnetic field is. So this is the way in which we measure. This is like the most basic way in which one can measure magnetic field. Now there are other ways in which one can do it. You can either sit at this dip here, or you can sit at the slope. That's, you can work with all these techniques.
Sorry, stupid question. So what is
No,
the
no,
typical?
no.
Yeah, what is the typical
Lambda?
delta lambda of your Photon line? Yeah.
Lambda, yeah. So this is 637 nanometer.
The width.
The width, yeah. So now the width can vary a lot. It depends. So if you have like the best crystals that are available, you'll get up to like tens of kilohertz line width. Okay. Now, if you work with very dense ensembles, you will never see tens of kilohertz line width. You will always see very, like the typical samples will have megahertz line widths. Okay, and so it really depends on which kind of system you're working with, and so
Talking about the luminescence,
Yeah, exactly. So
not about the microwave.
oh, okay.
in nano.
Oh, okay. The zero phonon line width, like the 637. It's a nanometer, about a nanometer. Few nanometers.
So
yeah.
because I was thinking about what is your resolution like when it's shifting? I mean,
Oh.
how?
Okay, so we don't care about that too much until you work with photons, right? Because what you're doing is when we want to do an ensemble measurement, we collect the entire red spectrum. So it's the spectrum actually starts from almost 630 onwards. So the zero phonon line is exactly at 637, and then you have it all the way up to 750 nanometers. When we put a filter just to cut out the green light, and then we put the long pass. So you essentially work with the entire red spectrum. If you're working with a single photon, then you have to filter out exactly the zero phonon line, which is about a nanometer or so lambda. So there you have to use the very narrow filters to separate out the real zero photon. Okay. Yeah, so NV centers, N and V. So now we have electron and nuclear spin, and so therefore you have a very nice and complex system, which has beautiful looking Hamiltonian, which has various different terms which correspond to magnetic field interactions, electric field strain, and temperature variations. So that means the more the number of terms, it's a catch-22. So more the number of fluctuations you will have in your system, and that means it can also sense all of these parameters. And because we have a nuclear spin for N14 variation, which is a spin 1 system. So spin 1 gives you a hyperfine corresponding to 2.16 megahertz splitting. And if you have an N15 nuclear spin, that's a spin half system, and it's 3.05 megahertz splitting. So this is the kind of system that we work with. So typically the starting point of our experiment is you just shine green laser and it will all go to ground state 0, 0. And after that, you apply your microwave and you can do all your cubic control experiments, or you want to do magnetic field sensing, so then you can perform the corresponding magnetic field sensing experiments there. Okay, now one interesting thing with NV centers, and since you had already brought up this NVs, there could be 4 possible axes, 4 possible orientation of the NV centers. And so if you have 4 possible orientations, that means that if you look at a vector magnetic field, which is an arbitrary direction, so you will get 4 lines on either sides of the zero field. So basically will correspond to each of those transitions from 0, +1, 0, -1 for each of these each of these levels. And so now you have a sensor which is not only magnetic field amplitude sensing, but also vector. You can do the full B field reconstruction because you have a lot of information on both sides with all these lines moving because of the magnetic field. Now you may ask, what about temperature and electric field and all of that together? Well, NVs are very nice, because they all move in various different ways because of these different kinds of applications. So if you have a magnetic field, then the lines actually move in two uniform ways in this direction about the zero field splitting. Then if you have electric field, you have a slightly different way in which the lines move. You can do a strain and then temperature. And so at least two of them you can do simultaneously. So that is what people have shown to date, that you can at least do at least two of them simultaneously. And magnetic field and temperature are the most common ones in which people have done simultaneously. So if you're interested, there is a very nice review article in Journal of Applied Physics where he has talked about various sensing modalities and all the different details of how to work with NV centers.
So is there a benchmark of what's the resolution of electric field that one can get? For example, in case of magnetic field, we know what the range is.
Yeah.
So,
There is a number. Yes, I just don't remember it all because things have been changing very recently. There was actually a paper which came up with one of the best numbers for electric field sensing.
I mean, for example, in quantum case, temporal squid gives temporal minus 15. These guys give about minus 12-ish.
I don't remember it.
No, I'm talking about magnetic field.
Magnetic field. Yes.
So is there a way to benchmark what my electric field sensitivity is to what would should be possible? May not be the. I mean, is there a way to sort of
For
say
electric field, I can't tell you off the because I don't.
the temperature?
Temperature, yes, it's a millikelvin range. You can get up to millikelvin sensitivity of people have demonstrated like 4 millikelvin per square meter temperature sensitivity. Yeah, electric field, I just don't remember the number. Yeah.
So I had a question about this. Distinguish between strain and electric field. Was one of the terms they look very similar.
Yes.
I know there was some paper.
Yeah. No, there is no real way to distinguish between strain and electric field. It's just that the way people have done the kind of measurement or what you expect would be the cause of, the change. So strain and electric field exactly have the same Hamiltonians. It's just that how, what have you applied to the sample? So if you do a bare bone measurement characterization of your sample, you inherently will see that there is strain. Because even when the diamond is growing, you will see that there is a strain pattern and due to which you essentially don't have uniformity in the sample itself. And that is because of inherent strain in the sample. That's not because of any electric field or anything, it's just pure strain. Now, if you now start putting, more pressure or do some sort of, mechanical movement, then that is a strain dependent measurement. Again, if you use it for electric field, it's up to the sensor person who's using it will actually identify what is strain, what is electric. Okay, let me jump directly into the quantum diamond microscope, which is essentially, if you have an NV center sample, you place whatever magnetic field sample that you would like to measure. So what it does is it changes. So if you remember, it's an N with an additional electron. That forms the NV minus complex, right? So it essentially what electric field does is it changes the electric the wave function around the NVs, and so it's like a charge coupling. So it's that's what couples into the next.
Effectively strains or something.
Yes, effectively that is exactly what you were saying. How do you identify between strain and electric field? So it's exactly the same.
So, sorry.
No problem. Yes, please.
Yeah. So you are talking about G2 measurement and all. So if I understand correctly, the light it's emitting, it's not classical. Some statistics is probably different from what.
If you're single NV, it's single photon. That's pure non-classical.
And are you also using those photons for some measurement?
Yes, that is a different set of measurements. Not today, not part of today's talk. Yes, we do measure single photons. Okay, so what we're working with, what I'm going to tell you today is, and maybe at the very end, I'll just show you what we are doing. So here you have an NV center, which is a bulk NV center sample. So which means it has a high density of NV centers. So about, to give you some numbers, about 10 to the power 10 NVs per centimeter cube. So that's a very high density NV center sample, which is a layer, and you can place any magnetic samples, which could be a 2D material, could be anything that has some magnetic features in them. And what you then do is shine the green light, collect the red light, either through a simple camera or a CCD camera. And what you then have is in the fluorescence is encoded the spin information or the magnetic field information. Right, so this is how we do measurement of or imaging with NV centers. And then, of course, you have to apply the microwave to drive these NV centers along with it. To give you some numbers, DC set, this is actually now very old. 50 picotesla is kind of higher on the side. So you usually now the best sensitivities are of the orders of 10 picotesla. If you work a little harder, you can get to 0.9 picotesla. Now this requires a little bit big work because you have to shield the sample and you have to take care of all sorts of electronic noise and many other things have to be taken into account. AC sensitivity is of course 0.9 picotesla because you're really trying to do some sort of a lock-in measurement or frequency dependent measurement, and therefore it sort of already narrows the bandwidth, and so you really can push it even further to get 0.9 picotesla. Spatial resolution, we are doing optics, it's diffraction limited. But you can also go into the scanning mode where you can get about 5 nanometers of resolution. But what is advantages is in this geometry, if you have like a microscope, so this is like a magnetic field microscope, just like a white light microscope, you can resolve, different features. Here you have a magnetic microscope which can resolve magnetic features, and so you can have a very large field of view, so almost 400 microns to cover 400 microns, and even very recently people have shown even millimeters of white field. NV centers, the delta B, the minimum resolution that you can get is dependent on the number of sensors. So the higher the number of sensors you have, the better it's like classical law of averaging. But what is important here is this T2 number, which is essentially the coherence time, or what is the fidelity of with which you can measure these spins, or how well can you measure these spins, and that's given by this number, which is the T2 star of our system, which is essentially the decoherence time of the system. Right? But what one can do is go beyond with the NV center, because these are ultimately quantum. You can really have interactions between, say, cavities and ensembles of NV centers and generate squeeze states or different kind of other entangled states. And that allows you to get the best kind of sensitivity in, achievements, and can go all the way up to N. And so many people are working with cavity-dependent interactions and of cavity-wide cavities with bulk NV center samples. And that's been one of the recent time focuses of many groups in US. To give you some applications very quickly, in bulk NV centers have been used for at low temperature because NV centers, although are room temperature systems, which is I didn't mention so far, these are all room, so far whatever I've talked about is all room temperature. You can do everything at room temperature. But however, it turns out that the most interesting things happen at low temperature. And so NV centers can work very well at low temperature because you in fact suppress a lot of phonon noise and all of that. And so people have shown that you can image vortices very nicely in using these NV centers. And for instance, in this graphene sample, you can do hydrodynamic current reconstruction flow with graphene with these NV centers. So this is that's the advantage of using NV centers, because you can actually do J reconstruction, not just B field measurement. Some other examples, room temperature experiments where this is not December, this is 21, where you can actually use like chips and other sort of samples which will have magnetic field features. You can look into very detailed analysis of magnetic field reconstruction. And some applications of biology. Here, this is a very interesting application where people have been looking into, ultra-sensitive diagnostic methods. So here, instead of using a bulk imager, what they've done is tagged a nanodiamond, which also does very good sensing, and you can actually see attomolar or zeptomolar, I think, sensing of various particles. There's another application in which you can sense, magnetic field inside living cells, and this is one of the key applications of MD centers, where you can look into, say, magnetotactic bacteria, or for instance, you can also look into temperature inside the live cell and probe local temperature. So these were some of the applications, and some of the recent applications have been understanding the magnetic field information in the cochlea of a bird. And as you know, that there are several birds, for instance, the pigeon hummingbirds, which sense the Earth's magnetic field somehow magically. The mechanism is still very highly debated, but MD centers have now shown that you can at least, there's a mechanism with which the birds are using their cochlea to sense this magnetic field. Another interesting application, this is what motivated me to start working on the imager that we are reading, which is essentially to look at neuronal signatures. So as a neuron, as we know that neurons interact through electrical pulses. And when electrical pulses travel down, any axon, for instance, in a neuron, or a wire, or electrical pulses travel down a wire, there's an associated magnetic field. So for instance, here in this is a live C. elegans worm, which has one single neuron. And in this, you can see that MD center, which is sitting underneath this neuron, has mapped out the axonal potential. And this is what prompted us to think of a way in which we can build a sensor which will detect mammalian cell neuron cells images. And this is what motivated us to think beyond just looking at single neurons, but a cluster of neurons. And
so is the magnetic field generated because of the electrical pulse? It's like an Oersted field, or is it something which is, there is a magnetic field associated with the neural signals? So what's the origin of this magnetic field?
It's just because of the current flowing through.
So that's the Oersted field.
Oersted field, yes, yes. Actually, I'll show you the. Yeah. So so going into what motivated us, and of course, I am not I don't work with biologists at all. We work with mimic devices which will somehow mimic neurons, and that's why we have taken a very spherical curve approach towards our problem, and simplifying all our problems down to wires and current carrying wires and imaging current carrying wires. And that's what we've been trying to build, which is essentially, if you have a network of current carrying wires, can you distinguish the location of the source of where what is the origin of the pulse, or can you image the pulse flow, etc. And that is what motivated us to devise these mimicked sort of patterns and trying to understand the current flow and the magnetic field from these mimic devices. We started off with a three-pronged approach. So we wanted to develop a sensor, then we want to work towards a prototype where we want to look into clusters of artificial neurons, and then hopefully go into single neuron or imaging of these with these MD centers. So the first thing that we in fact started when we started talking to biologists was that they in fact don't have very good understanding of what the magnetic field actually looks like inside the neuron. Because there's a whole bunch of structure to it, and if you really split, and neurons are of various different types, so they're not all of the same dimension, so all of them may have different kinds of magnetic fields. And what they had was just a bulk sort of an understanding of what the neuronal signature looks like. So what we started off was we split the real neuron structure into small isocompartments, and then integrated and found out what the net current flowing in them is because of the changes in the ions with sodium potassium changes. Now with that, we reconstructed the B field out of this, and interestingly, what the question that we wanted to understand is that how do these compartments behave? Is there any location where the magnetic field is actually higher than the other, and can we simplify the problem down based on what we can estimate from the actual neuronal signature? So this is the standard cable theory that has been developed, which is essentially to convert the neuron into a circuit, and from the circuit model estimate what the magnetic field is. So here we have actually split, instead of using a bulk lump circuit, we actually split it into smaller components and then integrated and found out what the B field that is going to look like, and then went on to actually understand how the B field will look like if an NV center measures the B field. Right. So that is what we are trying to simulate here. And what we found, interestingly, it turns out that if you actually measure right underneath this, this axons below, it turns out that the magnetic field is much higher than in comparison to the actual electric current that is flowing through the entire axon. So this, in fact, simplifies the problem down a lot, because now it's actually located in one and it's traveling, and we are able to be able to detect it much better.
How do you understand this? Is this related with how the electron flow is sort of, basically the density is increasing?
Yes.
Electron density.
Right. So here, because you can see that this is like the head of the neuron, so there is a lot of more electron density, and so that is our estimate that this is why we feel that there is a higher magnetic field.
So I don't think the booster field will change electron density when you are outside the system. Well, the moment you're outside, it has to depend only on the current. So I can't see how the density is.
No. So this is it's because you.
Inside is okay. So
Yeah. There are many channels here, right? So that's what is giving it this higher density. So we estimated about 30 picoteslas at a standoff of 20 nanometers. And so we said, okay, if we can measure this magnetic field, this is how the actual magnetic field profiles will look like if you do a full simulation of the field profiles. And you can see that it actually splits in two directions. It follows the natural. We've seen that it matches with the biological measurements very nicely, that it actually splits and goes in two opposite directions. And you can also see this is purposely made, that you can see that there's only one spot where it's actually very high density. And this is the map that the NVs will actually measure. So it will measure a very high density in one location. And so that gave us the idea that, well, if this is the case, then we should be able to build a dictionary of if you have a cluster of neurons or a volume of neurons which are located at some places, then it should have its own magnetic field signature. So that gave us the idea that we can build a dictionary, and in fact use one more information of that dictionary is that a neuron, when it fires, the axonal potential will actually last for several milliseconds. So we should be able to track that if their firing has happened from each of these special neurons. So we built a dictionary, and suppose if you have B, which is the matrix, which is essentially it's the measured, what will be measured with the NV centers. So we can do an inverse sort of a matching pursuit algorithm. We say that we locate a neuron only when we see the firing of 3 consecutive times, and then we subtract out that position and then fill in and do full reconstruction of the image. And this, in fact, with this algorithm, what we found out was that 2 neurons separated by about 10 microns is quite well recognizable by the NV centers. And what is important is it's not just the physical separation, but it's also the temporal separation of the firing. So if you actually have neurons which are firing simultaneously with the less than a millisecond apart, then we will not be able to distinguish the location. But if they are able at least firing at 1 millisecond temporal spacing, then you can see that the green dots match very nicely with the black dots, and that's where the neurons are essentially. And you can see here that at least 10 micron resolution is what we can get with the 0th order sort of algorithm that we have developed here. So this.
Sorry. So this is based on some experimental resolution with your machine.
Yes.
And what are the numbers you use?
Yeah, so we assume that we are at the best picotesla level sensitivity.
Right.
Yeah.
But with respect to your spatial pixel size and temporal.
Yeah, so that picotesla number is assuming the yeah, because that itself will tell you what is pixel resolution. So with this sort of motivation, we said, okay, well, there is at least some hope that it may work. So we went on to develop what is the sensor, and this is how our sensor actually looks like. You have a diamond which is actually glued onto a microwave antenna that we've custom designed, and then you shine the. So if you see, there's a hole in the center, so that's where the laser goes through, and on top sits the sample, which is the mimic sensor. So first, the thing we have to do is calibrate. And the first calibration we do is essentially perform the ODMR experiment. And as you can see, unlike my pretty picture in the first slide where you have all very nice, all uniform ODMRs, you of course don't get uniform ODMRs. Contrast depends on the magnetic field projection. It also depends on the number and also on the microwave antenna. So it really depends critically on the microwave antenna. So you see a lot of differences in this sort of, and you can also see that because of the alignment, you can see two predominant peaks and two smaller peaks here on one side. So if you zoom in to one of this ODMR lines, you can see the hyperfine splitting here very nicely. This is an N15 sample. So you can see the 3.05 megahertz splitting very nicely. And then you can go on and do the nice Rabi experiments where you can drive this qubits at one of these frequencies and continuously drive it, and you'll see very nice pretty oscillations and goes up all the way up to 8 microseconds and in fact even more. And if you work harder in setting up the magnetic field and all of that, then this will clean up even more. To calibrate the sensitivity, we are at short noise limited sensitivity of 150 picotesla per square root hertz. You can see that the T2 star is almost of the order of 1 microseconds. And this measurement has been done by what is called as the Ramsey measurement, where you first have a polarization pulse, you have a readout, and then you apply a pi/2 pulse, which brings the strings to the equator. Then you let it evolve, and then you measure again with the projection pulse of pi/2, and then you read it off with the green, because all our measurements are essentially done through fluorescence. And so then if you plot the, if you vary the time between these two pi/2 pulses, you plot what is plotted here in the x-axis, which is the duration. And then against the contrast, you see the very nice oscillations on the equator, which tells you what the decay tells you what the coherence time of the system is. And here you can see this is 1.1 almost microseconds. And that gives us a short noise limited projected sensitivity of 150 picotesla per square. You can go even beyond that, apply a Hahn, which is essentially just add a pi pulse, and then you can see these beautiful oscillations here. And that's because the electron spin and the nuclear spin are now interacting with each other. And so you can see a double resonance in the Hahn. And this gives us a T2 of almost 8 microseconds in the system. Another calibration that we can do is essentially just do a performance of the relaxometry kind of measurement, which is nothing but, sorry, this is not the correct one. So you can have just basically you have to vary the time. Between.
So the T2 is at room temperature.
These are all room temperature measurements. We don't have any low temperature system in our lab, so we do everything. Yeah, so everything is room temperature measurement. These are all measurements that we've done. So what you do is you vary the time between these two readoff pulses without the microwave. So you get one T1 measurement, and the other one, if you just have a pi pulse, which allows you to go to the one state, and then you look at the decay and do a measurement, which is relaxometry. And this essentially tells you that if you have anything fluctuating in the neighborhood of the NV center, you can also measure that fluctuation indirectly due to the fluctuations in the T1. And this is a very standard way in which people have been doing a lot of experiments with nanodiamonds, because nanodiamonds are harder to do in terms of pulse control. And so what people do is then avoid this microwave and just use the 2D light to do T1 measurements and look at the fluctuations in the T1 and see if there are any changes in the T1 because of anything in the neighborhood. And so even different sample variations, as you can see here, the contrast tells you that there are different density variations of the NG center, and you can see different points will have different T1 in them. Now, once you've done all the basic calibrations, you go on to graduate into what is known as the frequency modulated version. That's just one, it's like, going from the 101 to 201 level. And so once you start doing that, you essentially perform what is known as the frequency modulated ODMR. So that's nothing but you just sit at this point and you modulate the frequency and jitter that point and measure the fluorescence. And as you can see, what you will see is that because of this, you can perform what is lock-in measurement. So the jitter is where will tell you where you can actually essentially lock into. And once you do that, what you see is that in the ODMR spectrum now, instead of looking like two two nice Lorentzians will look like this, which is essentially a derivative of the Lorentzian. And so this is the ODMR spectrum if you do a frequency modulated version of the same, unless you're doing a simple frequency sweep. Now, this advantage of doing a lock-in variation is that you essentially get to sit at the 0-point slope, and if there is even a small shift in because of the magnetic field, it's much easier to detect. It's essentially like if you're doing a full sweep of the ODMR, you essentially have to sweep the entire frequency. But now you can sit at one point in the zero crossing field here, and if there is even a slight shift, you can measure that fluorescence and be able to detect that, and that gives you better sensitivity. One, and two, lesser noise, because this is lock-ins, because you're doing a frequency dependent measurement, and so you're really restricting to the bandwidth of that, and so you're essentially going to get better sensitivity.
But that's because it's very slow measurement.
This is not slow, this is fast, because you're at 1 point.
But you're using lock-in time constant, that's the speed at which each point is taken.
Yes, right, but that's much better if you compare the full sensitivities, then lock-in is better than like a full sweep. It of course gives you because you're just looking at one frequency, then you don't have to sweep the entire frequency range. So that in that comparison time is much higher, because it will take you several minutes if you sweep the entire frequency range, whereas the lock-in constant time is milliseconds. So you can just sit at 1 point and still be able to get much higher sensitivity. That's the advantage. Now, this of course, traditionally people were doing the bulk magnetic field sensing. So you essentially collect the entire red light, you send it to the photodetector, and then you do your standard lock-in measurements from the NV centers, the bulk fluorescence. Now, what we were interested was that can we apply this technique to the NV centers for imaging? And that's what we started doing. So just before that, single axis magnetometry essentially looks like this. If you have a field on versus off, it essentially just shifts the 0-point crossing. And so you don't have to really do the full sweep. You can just sit at 1 point at the highest slope and perform the sensitive magnetic field measurements. So here comes the interesting part which we have developed. Essentially is that instead of doing a full bulk magnetometry, we then started looking at imaging and get lock-in. And that's where you can see that this is actually pixel number. So now we have a CCD camera. We found this very nice CCD camera, which is a per pixel lock-in. So you can, for every pixel, be able to do a lock-in measurement. And so here you can see that there are 2 times 10 per 4 pixels, and each pixel now has a signature of the lock-in measurement that is performed on the NV center fluorescence. And so now you can really get, instead of doing a full CCD version, which would take several hours to capture one single snapshot of the magnetic field image, we have gone down to milliseconds of imaging time scale. And so that really takes the imager from being a static imager to a dynamic imager. So that's what we have developed here. And so I'll just tell you what the sensitivity numbers look like. So if you perform a full imaging sensitivity here, we are at about 120 micron plus 120 micron in field of view. And we get almost a sensitivity, median sensitivity is around 700 nanotesla per pixel. Okay, so per pixel, we have a sensitivity of this sort of deviation. Now, in the center, you see a hole. That hole has happened because we have burnt the objective with the laser. So that's why there is a hole in the image. Now let's go to imaging. What we have is, this is the real setup. You have a whole bunch of other things other than, of course, the microwave. You have to have the signal generator, which is the microwave. You have a pulse blaster, which essentially controls the timing and the triggers. And then you have the lock-in, which is the camera. And then you also have the computer and your DAC and everything to take the data, right? And then on top of all of this, we mount our mimic devices, and we put it right next to the NV center. And the most important factor here is the distance between the sample and the NV center layer. And that is what decides whether you're going to see a sharp image or you're going to see a blurred out. Right? And that is one of the most key parameters. And here we're using this sort of a structure, wire structure that we would like to image. Now, in reality, the lab actually looks like this. You have a whole bunch of optics. It's not just one straight laser going to the sample. You have to do a lot of work, and then you have the focusing objective. The sample sits on top. You have the magnetic field around it. You have the electronics, which is all put together. And finally, is to image these sort of samples, which look like this. We have envisioned this sort of a mimic device from the actual model of the neuron, which is it has a head and it has a tail. And so our head looks like this, which is a spiral microcoil, and it has a tail, which is a very long wire. Right? And what we have is a cluster of these sort of mimicked. Okay, so first thing we have to do is apply a current, map out the magnetic field. This is the estimated magnetic field. This is simulated at a standoff of 0. So essentially, we have the NBs right next to the sample, right? So if you simulate it, you will see that this is a single axis simulation, and then you have the Bx, By, Bz as would be measured by the NB center is what is shown here, right? So now let's look at the experiment. So we applied the 500 microamp current. Very well, it looks almost like what we would expect it to have. The fields match up very nicely. This is about 2 microteslas of field, and you can really go much lower than this. So we've gone even to nanoteslas here. So remember, 700 nanotesla per pixel is our sensitivity. So we reconstructed this. Static works out very nicely. Once static works out, we have to start working with the temporal and test our idea whether it is indeed true that we can do millisecond time scale imaging. And
Kasturi, so when you say reconstructed here, basically taking the image and from there finding out the Korean different vector.
Yes.
Components.
So you have diamond.
This is not the same reconstruction that you were talking about previously, right? So I just wanted to know.
This is NV reconstruction.
Got it.
That is the other one. Yeah. This is, so well, we then started modulating our B field or the current in this case, and very nicely we are able to match. This was a straight wire, so you can see that, this is about, we started off with seconds, 0.9 seconds, etc. And you can see that we can nicely track the magnetic field, and in the Fourier transform, we in fact see the harmonics as well, which is another key advantage of this measurement. Well, we went on to measure, of course, our nice looking neuron, mimic neuron, and you can see as you change the polarity of the current in this, with the polarity, you also see the magnetic field switching very nicely in the images. And if you do again the Fourier transform very nicely, you have the main peak as well as the harmonics also pop up. Right, so this gave us the idea that, well, now can we think of really pushing it not from milliseconds, but we have not from 30, 40 milliseconds. You actually have to come down to milliseconds because you want to do neurons at that point, right? So that is what we are currently working on, where we are trying to push towards making better and better imagers. But as you go through the entire process of reviewing, you realize that nobody likes periodically modulated signals. Everybody says that, hey, periodic works out very nicely. What about a periodic signal, because you're going to be measuring neurons? And so we said, okay, we'll modulate the current in that way. And let's look at the image. And here you can see, of course, the center part is blocked out. Here you can see that between this and this, that's where the transition actually happened. And you can see that in between is black. So it means that it's actually able to track the change of the magnetic field at least in 30, 40 milliseconds of time scale. Well, this is not the best because we are not at the best sensitivity yet. If we push the sensitivity, we will be able to get it better milliseconds of time scale. So
it's limiting your sensitivity right now.
There's a power.
Or you're not able to collect enough photons.
One, we are not able to collect enough photons, and also the excitation power. We are not saturating our NPs.
Oh. So you need to say the 700 nanotesla per pixel is what you would improve from.
Yes.
With the laser.
Yes. And the collection efficiency, of course, also. So if we can improve the photon collection efficiency, then we will also again improve. The other key important thing that we have to improve is the uniformity of the entire the field of view that we have. That is quite non-uniform so far. If we actually make it more uniform, it will be even better. The sensitivity distribution itself will be much better. So that is what people, so Ron Walsworth's group actually works on these double quantum protocols. And in fact, our comparison is with their protocol is that we are doing a single shot measurement and they are in fact doing, very high level complicated pulse structures, which are not required to reach the same kind of sensitivity level. But they claim that they can actually take care of temperature variations, which we are not able to. Here, there is still temperature variations that we work on.
What is the highest frequency with which you can operate your locking camera?
So the frame rate is 3,600, very high. We are not even close to that. So our sensitivity is not at all limited to the frame rate of our. One thing currently is essentially we are limited by the sensitivity of the NV centers. Right? We have to work on that. Yeah, so that with this idea, we filed a patent and we have been granted the patent for this. So now I'm going to show you a video because we've been talking about dynamics. Now, whenever we talk about dynamics, we want to see a video. So this is, you can see we have multi-coils here and you start, so you can really see real-time imaging of magnetic field changes inside this sort of sample. Now I'm going to shift gears and I'm going to talk about an application of using dynamic widefield imaging. So we started doing these micromagnet images. So here, how much time do I have? 5 minutes? Yeah, that's okay. I can. Yeah, I'll quickly sort of give a summary. Yeah, so this is a micromagnet. So these are formaloids, in fact. And you can see an array of formaloids. So we have a lot of these arrays of formaloids. And if you do a wide field image of this, it actually looks like these little dipoles that are sitting in these arrays. And so we asked the question that how can we use our dynamic imager to do some interesting measurements of this sort of magnetic samples, which of course, if you have a scanning tip magnetometer, you can image the actual features of magnetic field within the dipolar, within the magnetic field microscale structure itself. But if you still have this sort of an image, which is just a dipole, which is essentially the integrated magnetic field, what can you do with it? And that led us to this question of understanding, can we measure AC susceptibility with it? Now, AC susceptibility essentially requires that you apply a magnetic field at some frequency, and that frequency is far away. If you think of it with measuring with an NV center, it will never be within the dynamic range of your actual of your ODMR, because we're sitting at the slope and we have a certain dynamic range that we have to work with. Now, if you apply an external magnetic field, which is high field, then you really kick out from the ODMR. Right? So how do you counteract that situation? And my student actually came up with a very nice idea of using a voltage controlled oscillator. So what we can do is we can track the ODMR and then go sit on the slope and then be able to do AC measurements in this case. And so that's one of the very nice ideas that we came up with. And we started to look at what is the relaxation rate of this magnetization. So if you give it a kick, then you see how the magnetization relaxes. And so we worked with these formaloids and we did some sort of imaging with this. So this is what we see. The way we do it is we give it a reference pulse, then we put in an on pulse, which triggers the formaloids, and then we have an off. So once we have the off triggers, that means that if there is a remnant magnetization or AC because of the imaginary part, you should see something here. If you subtract out the off minus the reference part, you will see that susceptibility. So that will give us the imaginary part, and the on minus the reference will essentially give you the real part of your magnetization. So that's how we wanted to measure. Now it turns out what we see very nicely is that you can reconstruct the DC part of it or the real part of it very nicely. You see that in the image itself, which is essentially if you calculate the susceptibility, it matches very nicely with what is expected of the formaloid. But the imaginary part is empty. That's because the formaloids actually have a relaxation rate that is of the order of several kilohertz. And unfortunately, our VCO cannot be triggered at several kilohertz. So we have a problem there. But we are trying to understand if there are systems which can be still slower in terms of relaxation, then we can actually map out the entire real and the imaginary part simultaneously. So this is the proof of concept sort of demonstration. We can also, we've also been trying to do some sort of magnetic reconstruction from the current density itself and trying to convince ourselves that this is in fact true. And this work now we have written up and is now archived and also in view. So quickly, 2 minutes of what other things we are doing, which is essentially control of single qubits. So as I mentioned, single qubits, so we know that these are actually all singles. Here, this cluster here, these clusters here, these are all actually singles in fact. So this is a confocal microscope that home built, everything built, we built all, put together everything here.
Sorry, it will be very difficult to excite that single one on the experiments.
No, we do. That is what you see here. So if you look at our ODMR, we actually are able in that, of course, diffraction limited. We are diffraction, and that is why the spot size here is about 300 nanometers in the actual the spot that you see here. But of course, the ND is a single there because it's just scattering all over, right? So it's a 3 pi, 4 pi. So what you can see in the ODMR, so we've carried out the ODMR with not just a wire, but we have this a PCB which has a wire. You can see that the ODMR shows only 2 peaks. In fact, we scan the long distance to make sure that we are not missing out the other 4 peaks somehow, or other 3 peaks somehow on the other sides. And we know that because these are equidistant from the zero field, this is actually single NP center. So we've also done Ravi. You can see that this Ravi is actually kind of slow. It's 3.5 megahertz Ravi, but that can only be improved if we work on our, getting more power into the system so that we can trigger the NVs much better. So another work that we've been working with Professor Pavan Kumar in ISER Pune is essentially to track these nanodiamonds with gold nanoparticles and with very low optical power. That's the very challenging thing, is when you're doing optical trapping, you usually have to use higher powers. And here our goal is to trap with very low power. We've worked on this, and as you can see here, this is an NP center, and you can see it gets trapped very nicely with very low powers. And finally, to the conclusion, what I've shown you is that, we've discussed a little bit about what are the basis of this magnetic field microscopy and talked to you about this unique idea that we've implemented in making a dynamic wide field microscope. And then there's a small little side where we are working on essentially working towards single spin qubits. And what I didn't mention here is that it's not just single qubits, it's also hybrid structures which are essentially integrated with the spin photon structure. So we fabricate photonic crystal cavities, and we've been working towards integrating these photonic crystal cavities with these single photon and emitters as well as the spin qubits themselves. So we are in that process. And so I have to thank all the hardworking students. So Madhur is essentially the main person who has worked on developing the neuronal models, and the main magnetic field microscope is his work. And Shishir has helped him a lot. And Anuj is the person who has fabricated all the devices, all the fabrication. So 3 people work together, very close knit together to work on the magnetic field microscope. And Shishir is now extending it into higher frequency range. And Oyan is the person who's been working on the single qubit experiments along with my undergraduate student, Abhishek, who's developing various very interesting things, and maybe perhaps something I could talk next time when I visit. We've been seeing very nice work done by this undergraduate. Of course, none of this work is possible without the generous funding that I have received from IIT Bombay, from my seed grant, as well as DST, Inspire, SERV, and AFRL USA. And also the collaborators I worked with, Professor Shorbo, who is an IIT KGP, with the main person who initiated the Neuron project. And then we've gone into looking into various condensed matter systems with Sumiran and Prof. Berman and Shamashish, and of course the trapping work with Roman. So thank you very much for your attention. I'll be happy to take any other questions.
Any questions?
A quick one. So, this distribution of the MP, can you control that first, and if you can, would that be helpful?
Yes, the answer is yes and no for distribution. Uh, Sandia labs in US can implant very specific locations of the envy centers.
Yeah, femtosecond using femtosecond lasers.
Femtosecond laser is one possibility. The other is direct nitrogen implantation, targeted nitrogen implantation, and then annealing. So they can do to a precision of 5 nanometers is what they claim. I don't have that image here. I have samples with arrays of envy centers, so very well precisely test. Now it's still annealing is still a key step there. So it's not like even though you implant, you still may not have. So if you see an array, it may not be 100%, but at least you get some relative structure. But for most of the work that I've shown here, our samples are all just like bombardment of nitrogen with a certain density. It's not any pattern or anything.
And I mean, in your all your characterization, if it is uniform or some pattern that would improve something, you think?
That will improve if you are working with the hybrid, like the photonic crystal cavities, then we need the targeted implantation because you want the envies to be in the location you want them to be. Now, does it help if, okay, if I go back to this sample here that we have now with, look at this distribution. It doesn't help at all. Actually, I was very upset when I saw this because what happens is that when you have, like you mentioned, that it's difficult to, stay at that one location, right? Because there will be drifts in your laser because you have to remain within 300 nanometers, and that's very, very challenging, right? So what we do is we do active tracking. So we have our own course, so all software, everything written by the students, where we can do active tracking to a point, right? So that is how we can remain at one location. And this is world over in envy centers. You cannot do images or you cannot do experiments unless you track periodically. So this sample actually makes our life very hard because you don't have free space to do tracking. Tracking is essentially comparison between your neighbor. Right? And if you actually accidentally, you can go into this and skip into that. So that doesn't help. So usually the samples which are more sparse, denser, then it's sparsely spaced, envy center, then it's easy to work with. It's very difficult to work with this sort of a sample. And this is what we are currently observing. And you can see that, in fact, what we see when we do very long rabis, we never remain in the same place. And so we lose our contrast. Yeah. It's not because of the coherence time, it's because we are not staying at the same location of the envy center.
Maybe you could have an automatic stage that sort of tries.
We do. This is automatic. This is automatic. Yeah, everything is automatic. We don't do any experiment by hand. It's just impossible.
But I mean, that should take care of the drift.
Yes, tracking also. But in this sample, it is difficult to do that, even because you essentially have to remain within 300 nanometers. But even like a little bit of contrast here will essentially kick it out because you're not able to uniformly do it in all.
So, since we're talking about this tracking, you can deposit some pattern, very small pattern on the like you can use electron beam lithography using patterns. Just do white light imaging and always mark that spot.
Yeah, that is actually, I don't want to touch anything on the sample because I'm really afraid of losing the coherence time. And if you process the sample, usually what happens is any surface sort of termination changes the properties. So whenever you do fabrication on the diamond, so especially like for instance, if I want to do the photonic crystal kind of work, I don't want to start with a sample which already has NPs. I want to implant them after I have done all my processing, so that I don't introduce surface charges, which will actually, it has been known that surface charges because the fabrication actually degrades the coherence time. So that way, that is a little bit more challenging.
But you don't have to be like, you don't have to create many patterns.
Yeah, I know. Yeah, I know what you're talking about. So we are thinking right now, but yeah, it's a little bit more conservative on my side.
Oh, the question.
Yeah, so very nice inspiring. Congratulations. I didn't really get the answer to Arvind's question because are you measuring it near to when you're doing it? How far is the sensor from the device?
Very good question, because that really is one of the key limiting factors. When you really want to image the actual very sharp, clean structure, like for instance, I want to look at the current flow, like the entire reconstruct the entire current flow. I have to be nanometers away from the sample. Okay. If I want to do the J reconstruction, for instance, the reason I've shown you all the B reconstructions and not the J reconstructions is because we have a distance of about 5 microns from the actual current flow to the sample structure. So that actually allows us to, although we can see the image, the B very nicely, cannot do the J reconstruction because it's an inverse, right? So there, that the distance actually becomes a very key factor in the reconstruction. Now, however, for a neuron problem, we actually don't need that because we are only measuring like bulk magnetic field from one spot of. We just need to know it is there.
So, I ask this again. So, it's not the same electrical pulse that goes, but there is an associated sound wave that will expand, contract, expand. You're actually changing the geometry along with the electrical pulse. And how would that affect the magnetic? That's the, I mean, I know that
No, that we did not take into account. We just took, like, we just said that if there is an excitation, then you should have this electric pulse, and then that is the isopotential that we have just mapped out.
In this case, I don't think there would be any sound or acoustic pulse going around.
And also, I don't think that frequency will matter so much. We are measuring because we are anyway going to do log-in.
I would also like to congratulate highlighting the challenges in the experiments. I was curious to find out on your slide 31 what the power density that burned through that sample. Because very interesting observation.
Actually, when
What happened?
that's very. Yeah, it was my hard bond, I would say, because we damaged the objective. So essentially, what happened? Yeah.
I remember that.
Yeah, so it's a very.
The power density that.
Yeah, so actually, we used about 1 watt focused. This is not. Yeah, initially when we burnt this spot was actually because of the focusing, and then we changed our optics to not focus.
This is the average power you are talking.
Yes, 1 watt average power focused to a spot. This was about 100 microns or so.
Maybe there was a dot. That was.
Yes, it is very
The
likely
T
there
cell
was.
would not be damaged
I
by
mean,
that
no, but we did check with Olympus. In fact, they said that you are way above the, because this is a coated objective.
Yeah, way below the damage threshold.
No, we are way above the damage
Way
threshold.
above?
Yeah, we are way above the damage threshold. Actually, even like several, like 400-500 milliwatts is already way above, because if you're focusing very tightly, it's way above the threshold. And they said that you are really going crazy and don't do it. Then I asked, I said, well, but there are people I know who does it. And so what exactly do they, and do they also see objective burns? And then I went back and checked 2-3 theses. And I did see a fine print line which said we have damaged objective because we were not careful with the optics, and there were dust particles, and many things happened. And so a lot of people have damaged objectives, and we of course did. And since then we've been very careful, and instead of doing focusing, now we do back focus plane. So that allows us to take care a little bit more, but then that also means that we have to increase the power overall, because we are not saturating our LEDs. We are still at very minimal sensitivity. We have to push it down much better. Yeah.
So actually that sort of raises a question, see, just related with these burning objectives. When you do these experiments on these micromagnets, perhaps you want to use a different light geometry. You maybe want to excite the diamond. No,
yes,
not
so
actually.
that is side collection. So usually, not side collection, sorry, side illumination. So that is a way in which Ron has been doing, and he uses this side. But the tricky thing with that side thing is that you have to cut the diamond in a very proper, so you have to excite it in the correct angle to get the uniformity and the nice angle. So that optics is slightly harder than just doing straight out widefield, which is a slightly easier way. to work with.
There is a question from the audience, and just read it out from Dr. Amlan Mukherjee. I think you choose whether you want to answer this.
Okay.
It asks, one, what is the sample? Where is it from? And two, your comments on India diamonds, such as from diamond elements.
Okay. I choose to answer this very well. It's perfectly okay to ask this. So after begging elements for 4 years, they finally gave me the sample, which is from element 6. This is an isotopically pure carbon-12 sample with N15 isotopically pure. So it is one of the best samples available in the world. Of course, now apparently in the last 1 year, somehow they've magically made some more amazing samples which Paula has, which I don't have, so which I am now after. So again, another 4 or 5 years of begging, then maybe they will give it to me. The second question is how do the Indian samples compare? They don't compare. We are not yet in the position of comparing element 6 samples with them because there are several challenges. One is the purity of the gas that they use for growing the diamonds. That is very critical, and I don't think they have yet been able to solve this problem. And maybe from my knowledge, this is my experience with the quality of the diamonds is that although it is single crystalline, it is not the highest of purities. So that's one big problem, which means that the coherence time is always going to be limited.
But how different are they? How far are they?
So the diamond element samples are still bulk samples. I haven't tested a layer sample from them, so I don't know the layer sample. I'm talking, this is a layer sample. I also have bulk samples where I have coherence times of microseconds, and the diamond element samples are somewhere in the nanoseconds range. I have not seen anything that is very, very good. And if they have been working much harder, then maybe they would have developed something. I don't have any of their samples which that can be much better quality. So I don't know. So that's one thing. Yeah. So the diamond elements is, I think they're working very hard, and I know that they've been trying to develop this, but I feel the gas quality is a huge problem. And element 6 has worked very, very hard on developing the surface terminations, which they don't disclose to anyone. And they also have the layer technology, which is very, very different because it is not the direct implantation and healing our things. So even like the Tsunami samples don't compare as good as element 6. They are also still on the, but I know that Tsunami is ramping up quite a lot.
Which one is more difficult? Is it the implantation or just getting the pure diamond?
Pure diamond is possible.
It's possible.
Pure diamond is possible because with the CD technologies that are available, if you have the correct gas quality, even in India, if they actually have good gas quality and environment control, they should be able to grow very nicely. And I don't know, isotopically pure is another challenge because I think that gas is possible. Yeah, so I both reasons.
Let's finish this with the last question from online. And the question is, how do you achieve a uniform microwave field from the omega loop?
It's as uniform as you need. That is as much as I can say. The omega, of course, has a Gaussian looking kind of a profile. So there will be a region which is uniform, and there will be a region where it is going to have a sharp drop. We ensure that we are working where the field is uniform. And the way to know whether the field is uniform is you just measure the coherence time. It will tell you whether you're in the correct place or in the wrong place.
I think let's finish the meeting here, and before that, let's thank the speaker. Thank you. Oh, yeah. Please. Also, I want to announce that on this Monday, there is going to be a talk by Apurva on this year's Nobel Prize.
Thank you. Thank you so much.